Hi, welcome to Gases in the Ocean. Specifically, we're going to be talking today about gas solubility and exchange. So that's how and why gases move in and out of the ocean. So first off, why do we care, right? Why are gases useful? Well, they can be tracers for physical processes like mixing, deep water formation, we'll talk a little bit about that later, air-sea gas exchange, circulation. They also can tell us about biological processes, so like biological production, respiration, oxygen deficient zones. We also can learn a lot of things about atmospheric chemistry and global climate change, right? This is something that we're going to keep coming back to throughout the semester. And they tell us a lot about large-scale ocean changes. So like large-scale ocean oxygen loss is a concern right now and something that people are studying. And so there's some things that control gas concentrations in the ocean. One, air-sea gas exchange plus solubility, that's what we're focusing on today. We also have production and removal within the ocean. We'll be talking about that in a later video. And mixing in the ocean. We won't talk about that too much in this class, but it's something that can impact them. And so in this really idealized schematic up above me, we have air and water. And in the air, we mainly have oxygen, nitrogen, argon, which isn't listed there, but is present about 1%, and carbon dioxide, CO2, that you've likely heard about a lot. And so what we want to know is why do these gases move in between the water and air, and what controls that? So if we look at the composition of the atmosphere, we've got a table on the left with main gases in the atmosphere and then what their concentration is at equilibrium in the ocean. So there's some scientific notation here. Basically, for nitrogen, that's N2, our atmospheric mole fraction is 0.78. What that means is for one atmosphere, which is standard pressure, so if you have one atmosphere, 78% of the atmospheric gas pressure is due to nitrogen. And then when that equilibrates with the ocean, you have something like 420 micromoles per kilogram of nitrogen in the ocean. And so the table can be a little bit dry and hard to interpret. So I think it's a little easier to think about this in these little box tree plots up above me. And so in the atmosphere, you primarily have nitrogen, 78%, oxygen, about 21%, and argon, right, 78 plus 21 gives you about 99, argon about 1%. And so if you add up all three of those gases, nitrogen, oxygen, argon, that gives you about 99% of the gas in the atmosphere. Now in the ocean, you still have the same sort of relative amounts overall. You've got nitrogen is the bulk of it, then oxygen, argon is very little, and then actually CO2 is about the same as argon. And so you can see that you've got the same four main gases that comprise the main seawater concentrations, but their relative amounts are different, right? Whereas we have a lot more, we've got 78% nitrogen in the atmosphere. Once you go into the ocean, it's no longer quite so dominant. So we're going to talk about why that is. So a few things to sort of talk about beforehand. One is Dalton's law of partial pressures. And basically, first of all, what a partial pressure is. Partial pressure is the pressure of an individual gas. So if oxygen is about 20-21% of atmospheric pressure, and the atmospheric pressure is 1 atmospheres, the partial pressure of oxygen is 0.2 atmospheres, or 0.21. Basically, it's saying that if you add up the partial pressures of all of the gases in a volume, so for now the atmosphere, that will equal your total atmospheric pressure. And what this implies is that these gases, it implies ideal behavior, which basically just means the gases behave independently of one another. So if you have, let's say 0.8 atmospheres of nitrogen or 0.4 atmospheres of nitrogen, that doesn't impact how oxygen behaves. And so that means we can pay attention to one gas at a time when we're looking at air-sea gas exchange and how these gases move in and out of the ocean. So Dalton's law of partial pressures is a good thing to know, just sort of how the world works. And then gas solubility. And gas solubility is the solubility of a gas determines its partitioning between the atmosphere and the water. And so solubility essentially is how much gas water can hold. And so the amount of gas that's present in water for a given temperature and pressure and salinity is determined by the solubility. And so solubility coefficients are a type of chemical equilibrium constant. What that means is if you have water and gas or atmosphere that are in contact with each other and you let them sit for a long enough period of time, they will come into equilibrium so that the partial pressure of the gas in the air will determine how much concentration is in the water. And so the solubility determines the partitioning between the water and air. And so if we go back to then the difference between our atmospheric fraction and our seawater concentration, the reason that we have less nitrogen in the ocean relative to oxygen is that oxygen is about twice as soluble as nitrogen. So more of it can dissolve into the ocean for a given partial pressure. And so when you go from nitrogen in the atmosphere to nitrogen in the ocean, you change the relative amounts. Similarly for CO2, it's what's considered a trace gas in the atmosphere. It doesn't mean it's not important, it just means that it's present in a very small concentration. However, it's very, very soluble. And so once you get into the ocean, then the concentration, despite the fact that you only have a minute amount in the atmosphere, you actually have a significant amount in the ocean. It dissolves very easily. So just to talk about this solubility versus partial pressure again talking about oxygen and nitrogen. So oxygen is about 20% of the atmosphere, 20.9% really. Nitrogen is about 78% of the atmosphere. But if you look at the solubility versus temperature, oxygen is in the blue line up above and nitrogen is in the red line. Oxygen is about twice as soluble at any given temperature than nitrogen. And so when you take that and you look at the actual concentrations in the water, even though nitrogen is about 4 times more plentiful in the atmosphere, it's only half as soluble as oxygen, so the saturation concentration is about twice oxygen. So 4 times more plentiful in the atmosphere, half as soluble, so you have only 2 times as much nitrogen in the ocean as oxygen. So that's sort of the basics of solubility. Other thing to note, if you look at the solubility as a function of temperature, at colder temperatures, water can hold more gas. And so that's very important to how the ocean works and how it takes up carbon dioxide, how it exchanges oxygen. At colder temperatures, water can hold more gas. At warmer temperatures, water can hold less gas. So now let's say you change the temperature and suddenly the water can hold more gas. There's space for more molecules of gas in the water. It gets colder, solubility increases, it can take up more gas. How does it actually get into the water? Well, then we get into gas exchange. We're not going to go into any of the details of gas exchange parameterizations here, but you should know that cooling and heating influence whether there's gas exchange. Mixing with deep waters can, breaking waves, winds, wind speed, wave height, wave shape. You've got different kinds of breaking waves, whether bubbles are injected. There's a whole lot of things. Main thing though is wind speed. So at higher winds, you get more gas exchange. Lower winds, less gas exchange. And so what does that actually look like in practice? Right, so this is a video I took out in the Gulf of Alaska in the Northeast Pacific. And, you might just see waves here, but I look at this and I see gas exchange. I see bubbles getting injected into the water, waves are breaking, you're exchanging lots of gas and spray and everything between the water and the atmosphere. And so these kind of rough conditions, that's how you get lots of gas exchange and water and oxygen or CO2 moving in or out of the water. Okay, so to summarize our gas solubility and exchange, gases will move toward equilibrium between the ocean and the atmosphere. And that equilibrium is determined by the partial pressure of the gas in the atmosphere and the solubility of the ocean water. That determines how much gas the ocean can hold. And so if you're out of equilibrium, either because you have biological production producing oxygen and there's too much oxygen in the ocean, or if you have fossil fuels being burned and you're putting CO2 into the atmosphere and you have more CO2 in the atmosphere, then you're going to start to try and equilibrate between the atmosphere and ocean, and that's when gas exchange occurs. So once there's a difference between the actual concentration of the water and how much gas the water can hold, you get gas exchange. And gas exchange is faster with high winds and also breaking waves. Okay, so that's it for our intro to gases, solubility, and gas exchange. We'll talk a little bit more about carbon dioxide and oxygen in the ocean and how they operate over the next 2 or 3 videos. All right, thanks.